For 13.8 billion years, the universe has been humming. Not a sound you could hear. Sound needs air, and the space between galaxies is emptier than anything on Earth. But a hum all the same. A steady outward pressure woven into the fabric of space itself, pushing every galaxy away from every other galaxy with a force that never wavered. Physicists measured it. They gave it equations. They called it constant. The hum never changed pitch. Until now. In 1998, two teams of astronomers set out to answer a simple question. How fast is the universe slowing down? They already knew the answer, or thought they did. Gravity pulls, matter attracts. Everything that rises must descend. The universe was born in an explosion of light and energy, and ever since, gravity has been pulling it back. Like a ball thrown into the sky, the expansion should be losing speed, year after year, galaxy after galaxy, inching toward a gentle stop. Both teams measured the brightness of dying stars on the far edges of the observable universe. Both teams ran the numbers independently, and both teams got the same answer. The universe is not slowing down. It is speeding up. That discovery won the Nobel Prize. It also opened a wound in physics that has never healed. Because if the universe is accelerating, if something is pushing every galaxy away from every other galaxy with increasing force, then 70% of everything that exists is something we cannot see, cannot touch, cannot explain. We gave it a name. Dark Energy. Two words that sound like an answer, but are really a confession. We have no idea what this is. For 26 years, physicists held on to one comfort. Whatever dark energy was, it appeared to be constant, steady, fixed into the geometry of space like a tuning fork that never stops ringing. They were wrong. In the spring of 2025, deep in the Arizona desert, 5,000 tiny robots finished building the largest three-dimensional map of the universe ever created. 15 million galaxies, 11 billion years of cosmic history frozen in light. And when the scientists read what the map was telling them, the comfort vanished. Dark energy is not constant. It is changing. The hum is fading. And if it fades completely, it rewrites the ending. Not just our equations, not just our models, the actual ending of everything. This is that story. Let's begin with something most people get wrong. If you were asked to picture the Big Bang, you would probably imagine an explosion. A single point in empty space that blew apart, sending matter flying outward in all directions, like shrapnel from a bomb. That's not what happened. There was no empty space for it to explode into. There was no outside. The Big Bang was not an explosion in space. It was an explosion of space. Space itself, the fabric between things, came into being and immediately began to stretch. Every point in the universe was the center. Every point was the edge. The distances between things grew, not because things were moving through space, but because space itself was getting larger. This is the single most counterintuitive idea in all of physics, and it changes everything that follows. Think of it this way. Imagine baking raisin bread. You press raisins into the dough, and as the bread rises in the oven, every raisin moves away from every other raisin. Not because the raisins are crawling through the dough, but because the dough between them is expanding. If you were a tiny creature living on one raisin, you would look around and see all the other raisins receding from you. You might assume you were at the center of some great exodus, but you would not be. Every raisin sees the same thing. There is no center. There is only expansion. This is what Edwin Hubble discovered in 1929. Working at the Mount Wilson Observatory, perched above the haze of Los Angeles, Hubble pointed the most powerful telescope on Earth at fuzzy patches of light that most astronomers had dismissed as gas clouds within our own galaxy. They were not gas clouds. They were entire galaxies, vast cities of stars, each containing hundreds of billions of suns, each impossibly far away. And they were all moving away from us. Not just some of them, all of them, in every direction. The farther away a galaxy was, the faster it was receding. Hubble had discovered that the universe is expanding. Now, this was not entirely a surprise. 14 years earlier, a patent clerk in Switzerland had predicted it. Albert Einstein's general theory of relativity, his masterwork, his equations describing how mass bends space and how space tells mass where to go, had an uncomfortable implication. The equations did not allow for a static universe. They demanded that the cosmos be either expanding or contracting. There was no standing still. Einstein did not like this. The universe, he believed, was eternal and unchanging. So he added a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. It was a kind of anti-gravity, a repulsive pressure woven into the fabric of space itself, perfectly balanced to hold the universe in place. A cosmic thermostat set to exactly the right temperature. When Hubble proved the universe was expanding, Einstein was reportedly furious with himself. He called the cosmological constant his greatest blunder. He threw it away. He should have kept it. But we are getting ahead of ourselves. For the next 70 years, cosmology advanced on a simple foundation. The universe began in a hot, dense state. It has been expanding ever since, and gravity, the mutual attraction of all the matter in the cosmos, has been gradually slowing that expansion down. The only question was, would gravity win? If the universe contained enough matter, gravity would eventually halt the expansion and pull everything back together. A cosmic collapse. The big crunch. If it did not contain enough, expansion would continue forever, growing slower and slower, but never quite stopping. Galaxies would drift apart. Stars would burn out. The universe would cool toward absolute zero. The big freeze. Either way, the story had the same shape. The universe was coasting, slowing down. The ball was arcing back toward the ground. Measuring exactly how fast, that was the project. It was supposed to be straightforward. It was not. To measure the expansion of the universe, you need a ruler. Not a physical ruler, of course. There is no tape measure long enough to stretch between galaxies. You need something whose brightness you already know. Imagine standing on a dark highway at night, watching headlights approach. If you know the wattage of the bulbs, if every car on the road had identical headlights, you could calculate how far away each car is just by measuring how bright it appears. Bright means close, dim means far. Astronomers found their headlights in the deaths of certain stars. A Type 1a supernova occurs when a white dwarf, the dense remnant of a sun-like star, no larger than the Earth, but containing the mass of our Sun, pulls matter from a companion star. When the white dwarf reaches a precise mass, 1.4 times the mass of our Sun, it can no longer support itself. The star detonates. For a few weeks, a single dying star outshines its entire galaxy. 5 billion suns burning at once. And here is what matters. Because the trigger point is always the same mass, these explosions are remarkably consistent. Their peak brightness is nearly identical. They are the universe's headlights. In the mid-1990s, two competing teams, the Supernova Cosmology project, led by Saul Perlmutter at Berkeley, and the High-Z Supernova Search team, led by Brian Schmidt in Australia with Adam Rees, began hunting for distant Type 1a supernovae. Their goal was simple: find these explosions in faraway galaxies, measure their brightness, calculate their distance, and determine how much the expansion of the universe has slowed since the light left those stars. Perlmutter's team had spent years developing the techniques. Schmidt and Rees had refined them further. Both teams were meticulous. Both were cautious. And both fully expected to find deceleration, a universe gently applying the brakes. The data came in slowly. Photons that had traveled for billions of years, collected one by one on CCD detectors, converted to numbers, fed into models. And when the numbers resolved into a picture, neither team believed what they were seeing. The distant supernovae were dimmer than they should have been. Not brighter, dimmer. The galaxies hosting those explosions were farther away than any decelerating universe would allow, which meant the expansion had not been slowing down at all. It had been speeding up. Think about what that means. Throw a ball into the air. Gravity pulls it down. It slows, stops, and falls. Now imagine the ball slows, stops, and then accelerates upward, faster and faster, rocketing into the sky. Not because something pushed it, but because the empty air between your hand and the ball was somehow generating force. That is what the universe is doing. Both teams checked their data obsessively. They searched for errors. They accounted for dust that might dim distant supernovae, for chemical differences in older stars, for every systematic bias they could imagine. The result held. Perlmutter remembers staying up late at Berkeley, convinced there was a mistake. Rees, at his desk in the early hours, ran the analysis again and again. The numbers did not change. The universe is accelerating. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. But the prize was for discovering a mystery, not for solving one. Something was pushing the universe apart. Something powerful enough to overrule the gravitational pull of every atom, every star, every galaxy in existence. Something that made up 68% of the total energy of the cosmos. They called it dark energy. And in 26 years, nobody has been able to explain what it is. Let's be honest about this name. Dark energy sounds like science. It sounds like something written on a chalkboard, surrounded by equations, understood by someone smarter than you. It is not. It is a placeholder. A label we slapped on the universe's biggest secret because we needed to call it something. Here is what we actually know. Dark energy comprises roughly 68% of the total mass energy of the universe. Dark matter, a separate mystery, makes up about 27%. And everything else, every star, every planet, every person, every atom that has ever been observed by any instrument ever built, accounts for about 5%. We are not the main characters in this story. We are a rounding error. So what is dark energy? The leading candidate for most of the last quarter century was the simplest one. Remember Einstein's cosmological constant, the fudge factor he invented and then abandoned? It turns out he may have stumbled onto something real. If empty space has a built-in energy density, if the vacuum itself has a cost, then as the universe expands, this energy does not dilute. Matter gets spread thinner. Radiation gets stretched and weakened. But vacuum energy stays the same in every cubic meter forever. And since new space is being created all the time, the total amount of dark energy keeps growing, while the total gravitational pull of matter keeps shrinking. Eventually, dark energy wins, and the expansion accelerates.
This is elegant. This is simple. And for 2 decades, it fit the data beautifully. Observations of the cosmic microwave background, the afterglow of the Big Bang, mapped with extraordinary precision by the Planck satellite, were consistent with a cosmological constant. Supernova surveys confirmed it. Galaxy clustering measurements supported it. Physicists were not happy, exactly, but they were comfortable. Dark energy was a constant. The equation of state parameter, W, equaled exactly -1. The universe would expand forever, accelerating into a cold, empty future. But there was a problem. A catastrophic, humiliating problem that most popular accounts politely ignore. Quantum field theory, our best description of the subatomic world, predicts that the vacuum should have energy. So far, so good. But when you calculate how much vacuum energy there should be, using the standard tools of particle physics, you get a number that is too large. Not a little too large. Not 10 times too large. 10 to the power of 120 times too large. That is a 1 followed by 120 zeros. It is the worst prediction in the history of science. The calculated value of vacuum energy exceeds the observed value by a factor so absurd that it strains the meaning of the word wrong. Nobel laureate Steven Weinberg once called it the bone in our throat, the single most embarrassing failure of modern theoretical physics. Something is deeply missing from our understanding, and the cosmological constant, for all its elegance, offers no explanation. It just says, the energy is there, it is this amount. Do not ask why. Some physicists found this acceptable, others did not. And a smaller, more adventurous group began asking a different question. What if dark energy is not a constant at all? What if the hum has always been changing, and we were simply not listening carefully enough? This idea has a name: quintessence. From the fifth element of ancient philosophy, the substance that was supposed to fill the heavens. In this framework, dark energy is not a fixed property of space. It is a field, a dynamic, evolving entity, rolling slowly across its energy landscape like a ball rolling down a very gentle hill. Its strength could increase, it could decrease. It could do things that a cosmological constant never would. For years, quintessence was a theoretical curiosity, an interesting alternative with no observational support. The data kept pointing to a constant. And then, 5,000 robots in the Arizona desert started listening. The Sonoran Desert, 60 miles southwest of Tucson. The mountain is called Kit Peak by most of the world, but the Tohono O'odham Nation, on whose land it stands, calls it Yolcum Duag. It rises nearly 7,000 feet above the surrounding desert floor, high enough that the air is thin, the skies are dark, and on a clear night, the Milky Way arches overhead like a river of spilled salt. At the summit sits a white dome, 14 stories tall. Inside that dome, a telescope built in the 1970s, the Nicholas U. Mayall 4-meter telescope, has been given a new purpose. Mounted at the top of the telescope is a device unlike anything in the history of astronomy. It weighs 11 tons. It contains 500,000 individual parts, and at its heart, arranged in 10 wedge-shaped petals, sit 5,020 robotic fiber-optic positioners, each one holding a glass fiber thinner than a human hair. This is DESI, the Dark Energy Spectroscopic Instrument. Every 20 minutes, those 5,000 robots perform a choreographed dance. Each positioner swivels independently, aiming its fiber at a single galaxy millions or billions of light years away, with a pointing accuracy of 1/10 the width of a human hair. Light that left that galaxy when the Earth was young, or before the Earth existed, falls through the atmosphere, bounces off the telescope's mirror, and is caught by that single fiber. The fiber carries the photons down 40 meters of cabling into a bank of spectrographs that split the light into its component colors. And in those colors, the history of the universe is written. 20 minutes later, the robots reconfigure. 5,000 new galaxies. And again, and again. All night, every clear night, from dusk until dawn, DESI drinks in the light of the cosmos. To understand what DESI is listening for, we need to travel back to the very beginning. And here, the word listening is not a metaphor. 380,000 years after the Big Bang, the universe was still hot. A plasma of protons, electrons, and photons all tangled together. And through this plasma, sound waves, actual sound waves, rippled outward from regions of dense matter. Not the sound of anything in particular, the sound of the universe itself, vibrating. Pressure waves driven by the competition between gravity, which pulled matter inward, and radiation, which pushed it outward. The cosmos was ringing, like a bell struck at the moment of creation. Then the universe cooled enough for atoms to form. The electrons joined with protons to make hydrogen. The plasma became transparent. The photons streamed free. We still see them today as the cosmic microwave background, that faint glow of ancient light that fills every corner of the sky. But the sound waves froze. Their pattern, a characteristic ripple with a specific wavelength, was locked into the distribution of matter, etched into the arrangement of galaxies like a watermark pressed into paper before the ink dries. And that pattern grew with the universe, stretched by expansion, but always maintaining the same proportions. These are baryon acoustic oscillations, BAO, the frozen echoes of a sound that rang through the infant cosmos. Think about that for a moment. The galaxies you see in the night sky are not scattered randomly. Their positions carry the imprint of a sound wave that traveled through the universe when it was less than 400,000 years old. The universe is a musical instrument, and the song it played at birth is still written in the positions of 100 billion galaxies. DESI reads that song because we know exactly how large those sound wave ripples were when they formed. We can measure their apparent size at different distances, at different moments in cosmic history, and calculate how much the universe has expanded between then and now. It is like finding the same melody played at different tempos across billions of years, and using the change in rhythm to measure how the expansion has accelerated or slowed. This is what DESI does. It measures the Bow scale at different redshifts, different cosmic epochs, and traces the expansion history of the universe with unprecedented precision. The collaboration is enormous. Over 900 researchers across more than 70 institutions worldwide. The instrument was conceived in 2011, approved in 2014, and construction took years. The focal plane, that cluster of 5,000 robots, was assembled largely by hand. Gregory Tarlay at the University of Michigan led student teams that built 7,300 positioners, producing about 50 per day at peak effort. The precision required was at the limits of what production manufacturing could achieve. The project came in under budget and ahead of schedule. Then the world intervened. COVID-19 shut down the telescope for 9 months. In the summer of 2022, a wildfire swept Kitt Peak, forcing another 3-month shutdown. Damaged components had to be replaced, schedules had to be rewritten, but the collaboration persisted, because the question they were chasing would not wait. DESI began its survey on May 14, 2021. It was designed for a 5-year mission, targeting 40 million galaxies and quasars. By its 3rd year, it had already cataloged nearly 15 million objects, more than double its first-year dataset. Over 50 million spectra recorded, the largest spectroscopic survey in the history of astronomy. On March 19, 2025, at the American Physical Society's Global Physics Summit in Anaheim, California, the DESI collaboration released what it had found. The room went very quiet, because the song had changed. Before we describe what DESI found, let's be clear about what physicists expected. They expected confirmation. The standard model of cosmology, called lambda CDM, where lambda stands for the cosmological constant and CDM for cold dark matter, has been spectacularly successful for over 2 decades. It predicted the detailed pattern of the cosmic microwave background. It predicted the distribution of galaxies at large scales. It predicted the abundance of light elements forged in the first minutes after the Big Bang. Lambda CDM said dark energy is constant. The equation of state parameter W equals -1 exactly. It does not change. It has never changed. It will never change. DESI's data, taken alone, were consistent with this, and the collaboration was careful to say so. But here is where the story turns. When you combine DESI's measurements with data from the Planck satellite, the cosmic microwave background, something shifts. The best fit to the combined data prefers a model where dark energy is not constant, where W was more negative than -1 in the past, stronger than a cosmological constant, and has been drifting toward less negative values, getting weaker. Add supernova data, and the preference grows stronger. With one particular supernova dataset from the Dark Energy Survey, the statistical significance reaches 4.2 sigma. In physics, significance is measured on the sigma scale. 2 sigma, roughly a 1 in 20 chance of being a fluke, happens constantly and means very little. 3 sigma, 1 in 300, gets people listening. 5 sigma, 1 in 3.5 million, is the gold standard for discovery. It is what confirmed the Higgs boson. 4.2 sigma means there is approximately a 1 in 40,000 chance this result is random noise. That is high, but it is not 5. And this matters, because many 3 sigma results in physics have evaporated when more data arrived. Signals that looked tantalizing turned out to be statistical ghosts, born from noise and killed by precision. But there is a reason physicists are paying close attention to this one. When DESI released its first year of data in April 2024, the hint was already there, at roughly 3 sigma. What happened when they doubled the data? The signal did not weaken. It grew stronger. That is unusual. That is what real signals do.
Now, the details are stranger than the headline. DESI models dark energy's behavior using 2 parameters. W0 describes what dark energy is doing today. WA describes how it has been changing over time. For a cosmological constant, W0 equals -1 and WA equals 0. No change, no drift. A single, eternal note. DESI's best fit, W0 is approximately -0.7. WA is approximately -1.05. Translated into a story, this means, for the first 9 billion years of the universe's existence, dark energy was in what physicists call the phantom regime. It was stronger than a cosmological constant. Its density was actually increasing as the universe expanded, like a sound growing louder in a larger room. Most things become diluted as their container grows. Phantom dark energy concentrates. Then, roughly 5 billion years ago, around the time our own sun was forming from a collapsing cloud of interstellar dust, something shifted. Dark energy crossed a theoretical boundary called the phantom divide and entered a new regime. Since then, it has been weakening, diluting. The note has been dropping in pitch.
The phantom crossing is the part that keeps theorists up at night. Simple models of dark energy, a rolling scalar field, a single slow-moving particle, cannot produce this behavior. Crossing the phantom divide is supposed to be forbidden for the simplest theories. Something more exotic is required. Multiple fields interacting, modified gravity, physics that does not yet exist in our textbooks. DESI tried 4 alternative ways of modeling the data. They used binned analyses, Gaussian processes, physically motivated scenarios. None of them could make the phantom crossing disappear. This is not proof, but it is persistent. And persistence, in physics, is the first sign that you are hearing something real through the static. But science demands skepticism, and the skeptics have sharp arguments. George Efstathiou at Cambridge published an influential critique showing that the significance depends heavily on which supernova dataset you use. With one dataset, Pantheon Plus, the signal drops to 2.8 sigma. With the Dark Energy Survey supernovae, it reaches 4.2. A systematic photometric error of just 0.04 magnitudes, a tiny calibration offset in how we measure the brightness of dying stars, could produce the entire signal. Others point out that the W0WA model, taken at face value, implies negative neutrino masses, which is physically impossible. And some argue the phantom crossing falling precisely within the window of our observations could be an artifact of the parameterization, not a feature of reality. These are not dismissals. They are the immune system of science doing its job. And the DESI collaboration acknowledges every one of them. But the data keep pointing the same way, and the melody keeps shifting. If DESI is right, if dark energy is truly weakening, then the fate of everything changes. And I do mean everything. Every galaxy, every star, every atom. The entire future of the universe depends on what dark energy does next. There are three possible endings, and we do not know which one we are living in. The first ending is the one we thought we knew, the big freeze. If dark energy is a constant, if the standard model is correct after all, and the DESI signal fades with more data, then the universe will continue expanding forever, accelerating into eternity. The Milky Way and Andromeda will merge in about 4.5 billion years, forming a single enormous galaxy. But beyond our local group, every other galaxy will recede past the cosmic horizon, accelerated beyond the speed of light by expanding space. Their light will never reach us again. One by one, the stars will burn through their fuel. The last red dwarfs will gutter out 100 trillion years from now. Black holes will evaporate across timescales that make the current age of the universe look like a camera flash. And what remains is a thin, cooling fog of particles, each one alone, separated from its nearest neighbor by distances larger than the entire observable universe today. No structure, no warmth, no sound. The Big Freeze is a universe that forgets it was ever alive. The second ending is the most violent. The Big Rip. If dark energy were not weakening but strengthening without limit, then at some future moment, the repulsive force would overwhelm everything. First, it would tear apart galaxy clusters, then individual galaxies, then solar systems, then planets, then molecules, then atoms. Space would shred itself from the inside, taking everything with it. The universe would not wind down. It would come apart. This ending now seems less likely, given DESI's data. If dark energy is weakening rather than strengthening, the Big Rip retreats from the table. But what moves forward is the third ending. The Big Crunch. If dark energy is fading, truly fading, draining away like heat from a cooling engine, then at some point, gravity reclaims the cosmos. Expansion slows, stops, and reverses. The universe begins to fall back in on itself, slowly at first, then faster, like a breath being drawn back in. Galaxies blue shift, racing toward each other. The cosmic microwave background heats up, climbing through infrared, visible light, ultraviolet, X-rays. The sky gets brighter, hotter. Stars are pulled apart by tidal forces. Atoms are crushed. And in the final moments, all of space and time compresses to an unimaginable density. The end looks like the beginning. The last sound is the first sound. In October 2025, Henry Tai, a physicist at Cornell University, published a calculation that put numbers to this possibility. Using the DESI data and results from the Dark Energy Survey in Chile, Tai and his collaborators introduced a model featuring an ultra-light hypothetical particle called an axion. In the early universe, this axion mimicked a cosmological constant perfectly. But over billions of years, its effect weakened, revealing something hidden beneath: a negative cosmological constant. A negative cosmological constant means gravity eventually wins. Tai's model predicts the universe will continue expanding for about 11 billion more years, reaching its maximum size when the cosmos is roughly 25 billion years old. Then, contraction begins, and it happens faster than the expansion did. The universe collapses into a singularity at approximately 33 billion years of age. A beginning, a middle, an end. The universe as a story with a last page. Now, this is one model, built on data that is not yet at discovery threshold. Tai himself acknowledges that future observations could confirm or dissolve his conclusions. And other physicists warn that even if dark energy is evolving, its future behavior is unknowable until we understand what drives the evolution in the first place. We are at a crossroads with 3 roads, and the fog extends in every direction. But we are about to get better eyes. DESI is not alone. The instruments that will decide this question are already running or about to begin, and their combined power is unlike anything cosmology has ever assembled. The Euclid Space Telescope, built by the European Space Agency, is orbiting the Sun right now, 1.5 million kilometers from Earth, surveying billions of galaxies across a third of the sky. Its first cosmological data release is expected in 2026. Where DESI maps galaxies spectroscopically, measuring precise distances through the colors of their light, Euclid maps them through their shapes, detecting how dark matter and dark energy warp the images of background galaxies through gravitational lensing. 2 different methods, 2 independent ears pressed to the same wall. The Vera C. Rubin Observatory, perched on a mountaintop in Chile called Cerro Pachón, is beginning the most ambitious sky survey ever attempted. Over 10 years, its 8.4-meter mirror will photograph the entire visible sky every few nights, cataloging tens of billions of objects. It is named after Vera Rubin, the astronomer who proved that galaxies contain far more mass than we can see, the woman who gave us dark matter. Now the observatory bearing her name may help unravel dark energy. And NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will combine the depth of Hubble with a field of view 100 times larger, enabling supernova surveys and weak lensing measurements of unprecedented scale. If DESI's signal is real, if dark energy is truly evolving, then these instruments will hear it too. Multiple experiments using different techniques, observing different patches of sky, analyzed by different teams. That is how 5 Sigma happens. Not from one experiment shouting louder, but from many experiments, independently, catching the same change in pitch. And DESI itself is not finished. It is in year 4 of its 5-year mission, having surpassed 50 million total spectroscopic observations. By the time it completes its survey, the dataset will be larger still. 3 years of data took us to 4.2 sigma. 5 years may carry us further. Or it may not. The signal could weaken. The phantom crossing could dissolve into a calibration artifact. Lambda CDM could survive again, as it has survived every challenge for a quarter century. That possibility is real. But what matters is this: we are about to find out. Not in a generation, not in a century, in the next few years. The data are coming. The instruments are listening. And the answer is already traveling toward us, written in photons that left their galaxies when the universe was young. Step outside tonight. If the sky is clear, what you see is not the present. It is the past, arriving. Starlight that left its source years or centuries or millennia ago, just now reaching your eyes. Every photon is a message sent before you were born. The sky is not a picture. It is a letter, still being delivered. The nearest star beyond the sun is 4 light-years away. Its light left when you were making plans you have probably forgotten. The light from the Andromeda galaxy left 2.5 million years ago, before our species existed, when our ancestors were just beginning to chip stones into tools on the African savanna. And the photons DESI collects left their galaxies before the Earth formed, before the sun ignited, when the atoms that would become your bones were scattered through interstellar clouds that had not yet begun to collapse. You are made of material older than the ground you stand on, and the light you see is older still.
13.8 billion years ago, the universe rang like a bell. Sound waves rippled through a plasma hotter than any star, pressure and gravity locked in a contest that shaped the distribution of everything. Those waves froze when the cosmos cooled. Their pattern is still there, written in the positions of 100 billion galaxies, a signature so vast it can only be read by machines we build on mountaintops and send into orbit around the sun. And now those machines are telling us something we did not expect to hear. The hum is changing. The force that shaped the cosmos, the invisible pressure that filled every cubic meter of empty space with energy, that pushed galaxies apart and dictated the fate of all things, may not be eternal. It may be fading, weakening, draining away like the last heat from a fire that has burned since the beginning of time.
We do not know what that means. Not yet. We do not know if the universe will expand forever into silence, or tear itself apart, or fall back inward and end the way it began, in a point of infinite density, the last note collapsing into the first. We do not know. But consider this: one species on one small planet, orbiting one ordinary star among 400 billion, in one galaxy among 2 trillion. This species, fragile, brief, confined to a thin shell of breathable air on a world that has existed for less than a third of cosmic history, built a machine on a desert mountaintop that can read the frozen sound waves of the infant universe. And in those sound waves, they heard something change. Atoms assembling themselves across 13.8 billion years into minds that can wonder about the fate of all atoms. That may be the most remarkable thing the universe has ever done. The signal at 4.2 sigma sits just below the threshold of certainty. It hums with possibility. It refuses to disappear. The darkness is weakening. We do not know what comes next, but we are listening. And the universe, it seems, still has something to say.
This is Cosmic Canvas, where we trace the signals hiding in the static. Until next time, remember that 5% of the universe figured out the other 95 was hiding something. Never underestimate a rounding error.